Good morning. I am Aurora Mascolo, a PhD student at the Applied Physics group of the Department of Civil Engineering at the University of Salerno, and I give this talk on behalf of all the co-authors of the research that belong to the University of Salerno in Italy and University of Aveiro in Portugal. So, today I'm going to present the work entitled Noise Assessment During Motor Race Events, New Approach and Innovative Indicators. I will start with a brief introduction on the topic, and then I will pass to the research gaps and to the objectives of this work. I will then present the methodology and the case study and the results of the analysis, and finally the conclusions. So let's start with the introduction. Among all the pollutant threatening everyday human health, noise is for sure one of the most relevant. Specifically, as you can see in the graph reported in the slide and delivered by the European Environment Agency in 2020, in urban areas, the primary contribution to noise level comes from transportation, divided into road, rail, and air kind of transportation itself. In this regard, the effect of high-level noise exposure on human beings are widely studied and documented as short-term and long-term negative consequences. Although road traffic noise is the most impactful noise source, particular conditions that in a certain way involves it, such as motor race events, are not then investigated. In particular, these events are characterized by large sound pressure levels produced by sports cars, which usually are not required to respect the noise emission limit of the city cars. Taking into account the wide distribution of trucks on urban territory, it appears clear that the number of people exposed to this peculiar noise emission is not negligible, not only in terms of spectators and workers, but also citizens living nearby. In the slide you can find information about the homologating trucks present in Italy, which I came from. But how can we predict the total noise emission at a certain receiver of a motor race event? In this regard, this work reports a new approach presented by Pascale et al. Aimed at characterize the noise emitting during a motor race event by introducing two new acoustic indicators, namely LEL, that stands for lap equivalent level, and REL, that stands for race equivalent level. But why did we want to study this very peculiar aspect? We have to say that in the last decades, in order to assess the noise pollution, research focused on the road traffic noise modeling and evaluation. For this reason, there are only few studies on the impact of motor race events. Moreover, prior to the work of our team, made up by the collaboration between the University of Salerno and the University of Aveiro, there was no specific work in this regard, resulting in a lack of a specific parameter that could lead to assess the noise levels produced by a motorsports event. Such a parameter could lead to a better understanding of how the noise emitted during a race affect the exposed population and the surrounding area. All this considered, the main objective of this research is to develop, test and validate the use of this new approach and these indicators aimed at predicting the total noise emission at a certain receiver of a motor race event, just knowing the number and types of car involved. The most used indicator in literature and many regulation is the equivalent continuous A-weighted sound pressure level, where T stands for the time interval of interest, usually fixed by the regulation or by measurement's duration. Starting from this indicator, the research was mainly focused on the definition of these two new acoustic indicators named before, LEL and REL, in which it has been basically modified the measurement's time of interval into lap and T-race. Specifically, the LEL can be defined as the equivalent continuous sound level emitted at a certain receiver by a single vehicle in one lap of the track, and REL is the equivalent continuous sound level emitted at a certain receiver during a race by all the vehicles running on the track. This approach makes it possible to assess the noise emitted by an individual car during a track lap in the case of LEL, and by a group of cars during a race in the case of REL. As a case study, the circuit selected was the Circuito del Sele, located in the city of Battipaglia in Salerno, in Italy. As you can see from the table, the circuit hosts different kind of motor race events, such as car races, supermotard races, scooter races, kart races, and so on. In the slide, you can find the circuit pattern and its technical details, aside from the position of the points selected for the measurements, respectively A, B, and C. Point A is at 7.5 meters away from the central axis of the pit straight, where the cars are expected to reach the highest speed. Point B is at 15 meters from the roadway, near to chicane, where vehicle speed is expected to be particularly low. And finally, point C is situated at a turn, about 30 meters away from the roadway. Noise data were then collected using Class 1 sound level meters, as shown in the picture, and the equipment was properly calibrated before the measurements. These noise data were collected during two different measurements campaigns. In particular, the first one was held during a single vehicle test session of a Formula X car on 17 of February 2022. Then, thanks to the helpfulness of the circuit managers, we were able to take measurements during the official race day of the 12th Super Challenge Trophy. It was thanks to this collaboration that we were allowed to place the sound level meters at the edge of the track, as you have seen from the picture, in the area that is usually reserved for the sports and technical personnel, carrying out the measurements in safety. Now I want to show you very quickly some of the videos captured during the 2 days of measurements campaign. The first one is about the passing by of the single vehicle test session of the Formula X car on 17 of February. Let's watch it. The second one on the right is a clip recorded during one of the races that took place on 26th of March. Let's pass to the results. The recorded noise signal during the single vehicle test session of the Formula X car is reported in this slide, where values of sound pressure level are plotted against time. The vehicle drove around the circuit for a total of 17 laps. The graph, as you can see, clearly shows a peculiar trend, with peaks that are above 100 decibel periodically repeating through time. Such peaks clearly occur when the car passed in the proximity of the receiver. Since the lap race is almost constant, it makes sense to compare the distance between these peaks and the lap time. In particular, comparing the lap time estimation with information retrieved from the telemetry system, it was clear that the time distance between each peaks corresponds to a lap time. Then, based on the LP values measured, the LEL values were determined. Here in this table you can find information about the measured values of REL during the race session, respectively for point B and point C. As you can see, each column refers to a different category of the competition itself. REL values are generally higher at receiver C than at receiver B, since driver here were able to maintain a high value of speed, despite the fact that it was positioned at 30 meters away from the carriageway, while receiver B only at 15. But REL value also depend on other factors, such as type and number of participating vehicles, as you can see by comparing the values on different columns. For example, the fact that REL B values are higher than REL C values for N1400 and N1600 races can be explained considering that the related vehicles in these races were series-derived cars, characterized by a more efficient acoustic insulation of the engine, and for this reason, SARS receiver distance played a more predominant role on rel values with respect to the other sessions. So, generally speaking, we can say that the higher the distance from the track edges, the lower the record sound levels will be. If the receiver is positioned on a straight part of the track, rel will be particularly high thanks to the fact that the vehicle passes at full speed, generating a high sound level. On the opposite, vehicle speed could be particularly low along turns, and as a consequence of that, rel and rel values could be lower. However, it must be noted that in this part of the track, the drivers could sharply accelerate or decelerate, increasing the engine revolution per minute, with obvious repercussion on the rel and rel values. So, generally speaking, we can say that the choice of the receiver position is fundamental for a correct evaluation of rel and rel values. Here you can find sound pressure level recorded during the N1600 race at point B and point C, and rel values during this event. Also in this case, peaks are related to the car passing in front of the receiver. As it's shown in the graph, rel value tend to stabilize itself after about 2 laps by the race starts. In this regard, comparable values have been found for other races. So it can be empirically suggested that rel value during a race can be estimated by means of vehicle types and number and position of the receiver without using race time. With such a consideration, the authors propose to estimate rel value for a race by having the number of vehicle n and an average lap equivalent level at a certain receiver. This could work out assuming that the vehicle participating in the race belong to the same category and have nearly the same noise emission levels. However, rel values are not available for the vehicle competing in the races, this prevents the estimation of rel through the found equation. Nevertheless, during the GP Cup, in our case, a red flag occurred, as you can see from the two graph, and the race restarted with 2 vehicles less. It was then possible to us to compute rel values by inverting the equation and knowing car numbers before and after the red flag, by the mean of the rel values at the 2 receivers. In particular, the equation in the slide were the one obtained useful to simulate rel values at the receiver. Comparing measured and simulated rel values, it can be observed that rel value in point B and point C are overestimated by only 0.5 decibel in the first case and 1.2 decibel in the second case. Such results make it clear how well the identified correlation works and how these indicators actually can be used to predict the total noise emission at a certain receiver of a motor race event. So, in conclusion, the methodology presented allows to assess noise level produced during an event at any sensible, during a motor race event at any sensible receiver point. It can be applied at any circuit's layout and for any vehicle category to estimate how it affects the surrounding areas and the exposed population. The use of these innovative indicators can also lead to compare events characterized by different duration. Future works will be aimed at generating the noise emission curves for different sports vehicles in order to assess or simulate several operating conditions of the tracks. This procedure can also be used to draw noise map of the surrounding areas, both for existing and new tracks, with the advantage of separating the contribution of tracks operation from the other sources. In the slide, you can find one of a preliminary map that we had drawn of the Circuito del Sele, that will be more investigated and more studied in an upcoming work. In addition, these innovative indicators can provide new insights for the development of regulation for environmental assessment and protection, being more oriented at the real noise emitted by the circuits in the surroundings and be more effective for the estimation of the annoyance and of the risk for human health. Thanks for the attention, and for any curiosity or question on the work, feel free to contact directly me through email or Professor Claudio Guarnaccia.